Hello, hello, Professor. My name is Ishan, and today I will be presenting you the architecture of Raspberry Pi along with my team that consists of Jessica, Maria, Ethan, and Seth. So here's the overview of the presentation today. I'll be starting off with the introduction and the history, which will be followed by the architecture of the Raspberry Pi by Ethan, then the different models of the Raspberry Pi by Maria, and then Jess will be discussing the security vulnerabilities, and then Ethan will go over some of the relevancy to networking. Seth's going to present to you the future development possibilities for the Raspberry Pi, and I'll be giving you the conclusion. So, what is a Raspberry Pi? The Raspberry Pi is a computer that is the size of a credit card. It was initially created to be used as an educational tool to teach the youth low-level programming. However, soon after its release, the applications for the computer surpassed far beyond the creator of the device anticipated. Some of these uses will be discussed later in the presentation. Okay, so a little bit history about the device. This is Ibn Abdin, a British engineer who worked for Broadcom back in 2006. He started this computer as a hobby after being inspired by the BBC Micro created by Acorn Computers. He spent his time developing a portable and cheaper computer. During this development, he noticed a problem where the youth was being forced away from computer science, as computers were extremely unaffordable at the time. It was then that he decided to complete his project with the goal to make a small and affordable computer that can be used for educating the youth in computer science and teach them basic level programming. In 2009, he created the Raspberry Pi Foundation to further develop his product. The name originated from a trend that ran at the time with tech companies being named after fruits, as companies like Apple, Acorn, and Apricot Computers already existed. The Pi was added on as a reference to Python coding language, which was used to run the older models of the device. After working for After working on the device for 5 years, it was officially released in 2012 at an affordable price of $35. The product was an instant success, bringing in an astonishing 500,000 devices sold in only 6 months, all the way up to 20 million sold as of 2018, making it the best-selling computer in the general purpose category.
Okay, so architecture of a Raspberry Pi. So all models of the Pi, like the Model A and B, B plus, Pi 3, Pi 4, all the different versions of it, use the you have an ARM CPU built into it. And ARM is a architecture that's part of the reduced instruction set computing family of processor architectures. And that just means that it uses less cycles per instruction, making it more power efficient and therefore output less heat. So it's much easier to cool down and maintain it. Uh, because of that, the ARM architecture is purpose built for real time systems, embedded systems, and microcontrollers and computers like the Raspberry Pi. These are typically small systems you'll see in stuff like traffic lights and other embedded systems will usually have this type of architecture. It's also very often used in development environments as well because it's very lightweight, doesn't use a lot of power, it's easy to use and easy to learn.
Okay, so different Raspberry Pi models. So we've got three different models, Model B, Model A, and Model 0. Model B was the first one created to create a faster, the most complex Raspberry Pi. Model A was created after to have a cheaper model. In comparison, Model B is $35, Model A is $25. Finally, Model 0, which is half the size, a lot smaller, more compact, and that one went from $5 to $10. Much, much cheaper. So our next slide, we're talking about Model B, We've got 4 different versions of Model B, and Model A kind of followed suit mostly. Model B was the first one ever released in February 2012, and the board was only 85 by 56 millimeters. It came with a CPU, which was ARM at 700 megahertz, RAM 512, 2 USB ports, 8 general purpose input-output pins, HDMI RCA audio, and an SD slot, and only 10 over 100 Ethernet connector. Version 2 was released in 2015, and we upped our cores to 4. Then version 2B 1.2 released in 2016, 1 year after. The CPU got better, and we moved to a 64-bit architecture. Version 3B, released in 2017, pretty much the same as 1.2, but it integrated Wi-Fi and Bluetooth. On our next slide, we're going to talk about version 3B+, released in 2018 with 2 improvements. Our Ethernet got better, and our CPU always getting better. And version 4, our latest version in 2019, CPU got better. This time you have an option of RAM from 1 to 4 gigs, 2 micro HDMI ports, 4 USBs, 2 3.0, 2 2.0, better Ethernet, and better Bluetooth. On our next slide, we'll talk about Model A, created after Model B. First one was released in 2013. Very similar to the first model. The CPU is the same, RAM's just a little bit better. We've only got 1 USB port and 8 input-output pins with HDMI audio and SD slot. The 1A Plus was released in 2014, and we got more pins and micro SD instead of SD. Version 2A was skipped, but we went on to version 3A, released in 2018, and this one was the 64-bit architecture, 4 cores, a little bit better RAM, and this one included gigabyte LAN, Wi-Fi, and Bluetooth. And our next slide, the last Model 0. Model 0 was first released in 2015, half the size of Model B, with a CPU, ARM 1 gigahertz, RAM 512, 1 micro USB port, 17 pins, and 1 HDMI. And that one was only $5. The next one released was the 0W for $10, but that was because it included Wi-Fi, Bluetooth, and a camera port built in. And finally, the 0WH, pretty much the same as the W, but it also had a pre-soldered input-output header.
A study done at the National Distance Education University conducted an analysis on the security vulnerabilities of both the hardware and software components of Raspberry Pis. They found the following hardware vulnerabilities: USB power and backfeeding, overclocking, GPIO logic levels and serial access, real-time clock absence, and Xenon flash shyness. And the following software vulnerabilities: default user and password were created, network ports left open, and services left exposed. I'll go on to explain some of these hardware vulnerabilities. So a vulnerability was found where a USB hub can be used to backfeed a Raspberry Pi. Backfeeding allows the Raspberry Pi to be fed by the incoming current from USB ports, effectively being able to fry a Raspberry Pi due to the lack of USB protection in the design architecture. The GPIO logic pins is another hardware component with a security vulnerability on the Raspberry Pi. This is due to lack of protection mechanisms against overvoltage. Any incoming voltage of higher than 3.3 volts can destroy the computer. Raspberry Pi systems are designed without real-time clocks to reduce costs. By not having a real-time clock, date and time do not exist in any internal storage, which is essential for certificate validation of cryptographic actions. So this becomes another vulnerability. Finally, Xenon flash shyness as a vulnerability. It was discovered that the Raspberry Pi 2 reboots if a laser is pointed at it. In Windows 10 IoT, the default installation leaves 8 ports open and their services: FTP, SSH, web server, and WinRM. If the operating systems installed on a Raspberry Pi are left with the default configuration, such as unrequired services left open or ports left open, the vulnerability of the system increases. The study concluded that the Raspberry Pi hardware design is more focused on decreasing costs than it is focusing on securities. Users should be mindful in this goal and focus their own efforts on securing the Raspberry Pi.
Okay, so relevancy to networking. A big thing Pis are used for in industry is penetration testing, because they can be used as little subtle devices that you can plug into Ethernet ports you found unguarded and with no proper security policies. You can leave them and connect to the Wi-Fi, and do a bunch of different things with them. There's something called a LAN tortoise, which is essentially a Raspberry Pi, same architecture, and that's used to capture all the traffic going over a LAN essentially. It's also very used very often in research purposes because it's a cheap platform and you can get a lot of them pretty easily. So if you need to emulate a lot of real physical hosts, it's very good for that. And if virtualization isn't going to work, it's a good example of it being used in a research setting is for cloud computing and cluster computing. There's a project called the Octopi where there's like 8 Raspberry Pis set up, and they each essentially are their own thread when a program's running, and not instructions. Yeah, instructions are sent out to each different Pi like a cloud computer would. They're also very common in IT environments because they can be used as like a lightweight DNS server, DHCP server, NTP server, lots of different things. They're not very fast and powerful though, so in an enterprise environment they aren't typically used, but small businesses you will use them very often because it's much cheaper to buy the $100 Raspberry Pi, configure it yourself, than to get like a managed $1,000 router or something like that, or server to use for a small business. Another thing they're used for pretty often is remote access. Is essentially just being a VPN endpoint that you connect to, and they just act as like a tiny router. Once again, it's good for 1 or 2 users. It's not meant for enterprise VPNs by any means, but it's good for small businesses and things of that sort. And that kind of relates to penetration testing because it can be set up as a remote access to a subnet that you normally need physical access to because you can just set up the Pi. And there's lots of development boards for the Raspberry Pis, so you can do lots of different things with them. There's development boards for networking specifically to give them a lot more physical ports. There's also other cool things like cameras and environmental sensors that you can hook up to networks to feed data to a centralized server.
I'm going to be talking a little bit about the future development possibilities for the Raspberry Pi. By analyzing other competing models, we can see what they are doing better and draw some general conclusions as to what the future of the Raspberry Pi could potentially be. The first primary conclusion comparing these two boards is the fact that the Raspberry Pi could definitely increase their processing power going forward. According to Moore's law and other similar theorems, the processing power is only going to get higher as computers get less and less expensive, and while most companies have moved away from following Moore's law strictly, it is still the case that by way of die shrinks and development of new processors, we're going to get more computers naturally as time goes on. This means that we're going to see more and more smaller, powerful boards coming from Raspberry Pi and their competition forward. Potentially more exciting developments come from the potential for enhanced user development. Shields and peripherals can be used to enhance any of these devices. You can put a Raspberry Pi shield onto a Raspberry Pi and add new hardware functionality that they don't necessarily have. The key area for establishment here is that, similar to these Raspberry Pi shields, competing architectures offer the addition of Arduino shields as well. These Arduino shields are used primarily for working with Arduino microcontrollers, which means that they offer quite a bit in terms of scalability of hardware to integrate this into your own circuits. If the end user is designing FPGA boards or other similar products that could be interoperable as small computers or processes within the context of this larger architecture, then the expansion with these Arduino shields is incredibly useful. As these architectures become more and more modular, you're going to see more use cases. The more you can add and take away as per the needs of the end user, the more it's going to be useful for them. You can see enhanced Raspberry Pi usability in potentially corporate settings as a result of this, or places where development or a more specialized board would be used. Potentially the most interesting of these development possibilities is the increased tendency to be using Raspberry Pis and single board computers as personal computers, with the Latte Panda offering a small amount of internal storage that is local to the board, as well as enhanced operating system support. You can sort of see the trend developing that its potential to use a Raspberry Pi as a PC. These are very budget computers, and so you can imagine that there would be use for any of these devices in a school context where you need a lot of devices that don't necessarily have to be the most cutting edge in terms of processing power, or places like libraries where you need simply web browsing and to access databases. You can sort of see this already starting to happen with some people having replaced their personal work from home computers in their offices with Raspberry Pis. The Linux software support offers quite a bit in terms of ease of use for end users, and there is potential there that this could, going forward, ultimately replace home computer usage.
In conclusion, we talked about the history of the Raspberry Pi and how it's the best-selling general-purpose computer since 2018. We discussed the architecture and different models of the device. We explored how it's more focused on decreasing cost than developing security. We looked at different network applications for the device, and we went over future prospects for the device. That's everything from us. Thank you for listening.